Hi everyone. I'm trying to record this video to help you to study the structure determination problems with the infrared spectroscopy and also the NMR. Um, there are problems that I have uploaded it in the e-learning, and then some of them are easy, some of them are not. These problems are something that you can always do yourself first and then trying to find out what you can do with it. And I'm trying to show my way of thinking so that you can check that whether you are on the right track or maybe you need some more information or you need more examples and practice and things like that. So I'm going to share the PowerPoint that I prepared for using one of the problems that I uploaded it in the e-learning, and then I'm trying to show you how I solve these problems. Hopefully, this give you an idea that what sort of things that you need to pay attention when you see the problems like this. Okay, so going for the PowerPoint. Oops, that. Okay, so this is the first question. Um, what do we see here is this very small molecule, right? Because you can see it in the screen. It has only the 3 carbons and 5 hydrogen, 1 bromine, and O2. So probably what we can do first is trying to calculate what is the degree of unsaturation of this molecule. That will be the number of the carbon, which is a 3, subtract uh, 5, I mean the number of the hydrogen, and it's also number of the bromine as well, half the number of the bromine. So 5 plus 1 divided by 2, and then oxygen does not prov uh, increase any degree of unsaturation. So, and then we just have to plus 1. So this will be 3, 6 minus 3 plus 1. So we have a 1 degree of unsaturation in this molecule. So which is just a 3 carbons and 1 degree concentration, probably a double bonds. But I wouldn't exclude the possibility this may be the cyclic molecule as well. So we don't know whether this is a 1 degree concentration coming from double bonds or the cyclic structures. Right now, what IL shows us is a very broad band on 3000, right? When you see such a broad band on the 3000, and that is a clear indication that we have a carboxylic acid. So this is definitely a carboxylic acid, and we can, if it is carboxylic acid, this is a OH stretching signal coming from the carboxylic acid. Then we need to see the carbonyl, the CO band as well, and that is right there. So we definitely see that these two bands is pointing out that this is definitely the carboxylic acid. So let's try to figure out, what is left there to find out. The C3H5 and 1 bromine and then 2 oxygens and then COOH, that's C1 and definitely 2 oxygens and 1 hydrogen. So what's left out, since we already figured out carboxylic acid, we need to figure out C2H4 and then 1 bromine. And we didn't cover the mass spec, but these two peaks, only the 2 mass apart, that's clearly indication of the having a bromine there. But our molecular formula already showing the bromine there. So this is a sort of like not a very useful information right now. So what could be the C2H4? Well, now let's go for the NMR and trying to see. First of all, we have 3 carbons in the molecular formula, and if you look at the carbon 13, we have 3 peaks. So that means these molecules are probably not symmetric. That's why we see all the 3 carbon peaks in the carbon 13 NMR. If you're wondering what are these carbon peak, why didn't I pick that one? That's a CDCl3. we talked about in the carbon 13 NMR, these the NMR solvent is also shows up. That's about centers about 77 ppm. That's the typical key signature of the CDCl3, the carbon 13 peak. So this is definitely coming from the solvents, and then we got three peaks over there, and then one's a little bit more de-shielded compared to the other. So probably this is the carbon maybe that bears a bromine. Um, well, and then we have a 178. That's the carbonyl of the carboxylic acid. I think that's the what this makes it. So the what else we can tell from the proton is this very broad exchange signal. That is this proton of the carboxylic acid is basically showing this one very broad, also exchangeable proton there. Two hydrogen on. So that means this is a CH2, and then that is definitely CH2 too. So it's a pretty small molecule. So I mean, there's I mean, each carbon is there's a this basically CH2 CH2, and it's kind of hard to see, but looks like a triplet, right? That looks like a triplet too, so that support the CH2 systems. And then what else we found out from the slides? We have the carboxylic acid, right? And then we have the bromine there. So if we connect all these things together, so bromine goes there, this connects there. So I think this molecule is basically these structures. That way, you can see that there's a two CH2, CH2. I mean, there that would be the one day showing up in the NMR, the proton NMR, right? And those two will be this one, and the carboxylic acid and bromine. So this is a pretty simple one to go over at least. So I think that would be the answer for this one. For the second question, what do we see here is a C8 H1404. Well, compared to the what we did the previous one, this is a pretty large one. Let's do the degree of unsaturation again, which is number of carbon, 8. Half of the hydrogen, we substitute half of the hydrogen, so which is a this, and oxygen doesn't count, so that is a that will be 2. So we have a 2 degree of unsaturations. Um, Again, where the degree of saturation can come from, that will come from the maybe the pi bond, or it can come from the cyclic structures. Um, we don't know what it is, so we have to take a look at it. But right now, uh, we see there's a 3000 line, right? There's a 3000 line, and then there's a no peaks above, no bands above. So probably we don't have any carbon-carbon double bond, or I mean, at least the hydrogen and carbon-carbon double bond. I don't think we have that. So we got carbonyl, and which is a 17, close to 50. So this is a clear indication we have an ester. So we have an ester. And then if you look at that, I mean, how much oxygen ester takes it is a CO2, right? One ester functional groups takes 2 oxygens, but we have a little bit unusually large number of oxygen in the molecule, 4. So potentially we may have a 2 ester. So we may have a 2 ester. I mean, if this is an ester, that basically accounts for the 1 degree of unsaturations. And then if the 2 ester, then there will be 2 degree unsaturation. So these basically accounts all the degree unsaturation, but we don't know whether there is a 2 ester or 1 ester. How are we going to figure that out? We need to see other things, which is a NMR spectrum. We have 8 carbons. So in the carbon 13 NMR, if the molecules are not symmetrical, we should see the 8 peaks. But if the carbon 13 NMR 1, 2, 3, 4, 5, we have only 5 peaks for the carbon 13 NMR. So that means we have some kind of a symmetry in the molecule, especially um, the proton area. If you look at the proton area, proton NMR, this clearly show that this is the 4 hydrogen, not just two, right? Four hydrogen comes together. So there's no way was one carbon have a four hydrogen and then be a part of another molecule. So what that means is this is a two CH2 happen to be uh, comes together because of their equivalent. And then again, the six hydrogen, and there's no way you can have a six hydrogen in the one carbon. So this is a two methyl groups happen to be in an identical. So that's why we definitely have a symmetry in the molecule. And then if we look at that, this pattern, this Q means a quartet, T means a triplet. I know this is a four hydrogen, this is not a two hydrogen, but if you remember that the two hydrogen is a quartet, three hydrogen on the triplet, that is a kind of an indication that it's a ethyl groups, right? It's a four hydrogens. What that means is that with the two groups of the ethyl, right? The CH2 and CH3, these becomes a quartet because it's a split by the three hydrogen, and that becomes a triplet. And then this is a two hydrogen, there's a three hydrogen, but if you have a two groups, then that explains why we got the four hydrogen and six hydrogen over there. So this is definitely two ester, and I mean two ethyl groups. And then one of things, clearly showing that the chemical shift of this part, the CH2, this is a definitely over four. What that means is this is probably next to an oxygen. So one way, I mean, so that means that we could have a two ester. I'm gonna connect the carbonyl that we found earlier. So this is definitely a part of the ester groups. So we got these. We have a two of them there, right? We have a two of the ester there. And then this symmetry in the molecule also point out that the carbonyl, this carbonyl of the ester, we only see only the one, the CO, the carbon peak. So that means that definitely these esters are symmetrical. I don't know how it looks like. It's a symmetrical. So I'm gonna show it like this, ester bond here, and then whatever it is, we got symmetrical situation there. I don't know what's in the middle, but these two esters are symmetrical. That's why these two carbonyl comes as a one. This is a CH2 next to an oxygen also comes as a one. We only see one groups of carbon showing up there because symmetry, and then this is also two. So then let's try to figure out what's left out. So the molecular formula is what? C8H14O4. So C8H14O4. So if this is the case, then what? So how many carbons in one, two, three carbons and five hydrogen and two oxygens in the one ester. So we got two of them there. So C6H10 and O4, right? So that's what we found out, two ester groups, two ethyl ester. And then we substitute out, we found out C2H4 is left to be found out. So two carbons and the four hydrogens. I mean, two carbons and four hydrogen, that could be CH2, CH2, or it could be CH and CH3. There's a two possibility there. Which one is what in the molecule? That clue is in here. We got one hydrogen, which is a quartet. What that means is that this one hydrogen having a three hydrogen in the neighbor, right? And then this is a three hydrogen, which is a doublet. What that means is it is a one hydrogen in the neighbor. So if you look at that one, this should be triplet because there's a two hydrogen next to it. So triplet is what we need to see if that's the situation, but that's not what we see there. So only possibility that support that NMR is this one, not that one. That way, this hydrogen is going to be the quartet, and then that's this quartet right there. And then this hydrogen is going to be doublet, which is have a doublet right here. And then why these ones are so de-shielded is because this CH is going right there. So if I write down the complete structure, then you're going to see why it's going to be such a D-shielded. So we got ethyl ester, and then the CH comes there, and then CH3 is here. So this one having a or surrounded by the two carbonyl, so it's supposed to be de-shielded significantly. So that's why it comes up in the chemical shift. And so this is a structure of this molecule. So this is a kind of a little bit complicated because of symmetry, but this is telling us that we have to look at things very carefully, especially when you see the less number of the peaks in the carbon 13 NMR, then you have to suspect that there is a symmetry there. Okay, so moving on. So next one is C9. So we got large number of carbon and just H12. So degree of unsaturation, if you calculate it, so 9 is number of carbon and then half of the hydrogen, so 12 divided by 6 plus 1, so that would be 4. So we got 4 degree of unsaturations. So that's somewhat significant. Um, in the NMR, what we do see here, well, we got some kind of a this unsaturated signal, right? Hydrogen on double bonds. But this double bond can also be a part of the benzene too. So we don't know whether this is just regular double bonds or this is a benzene. One of the signal that is supporting is this C carbon carbon double bond. Normally 1660, but when it's a part of the benzene system, because of the resonance structures, this carbon-carbon double bond stretching signal becomes a 1600. So this is a sort of like a suggesting we have a benzene, but obviously if it's a benzene, then NMR will show the aromatic, the hydrogen. And then clearly we got 5 hydrogen in the aromatic region. So this is a definitely the benzene, right? And then 5 hydrogen means that we got 5 hydrogen there. It's just a monosubstituted benzene. And I don't know what it is, but something else should be connected there. So, and then also this is a 4 peaks in the carbon 13 NMR 1, 2, 3, 4. That is a basically supporting the benzene. And then we got 3 aliphatic hydrogens. So we got 6 carbons from there, and then 3 of them. So that uh, accounts for the 9, right? So these 4 degree 1 saturation, that is definitely coming for the benzene. Benzene account for the 4 degree 1 saturation because of 3 double bonds, and then 1 the circular structures. So that is 4. So basically, that's how we found out. Now we have all degree 1 saturation accounted it, and then benzene about 6 carbon, and then somehow we got 3 carbon chain. That this is what we need to figure that out. At least we know there's a benzene, and then we need to find out this is 3 carbon chain. How does it gonna be look like? Well, the clue for that 3 carbon chain is coming from there. This is CH2, right? This is CH2 because there's 2 hydrogen there, and there's a 2 hydrogen, there's a 3 hydrogen. So that means that this is CH2, there's a CH2, there's a CH3. Well, it's kind of hard to see, but if you look at the CH3, it sort of like it becomes well, it says right there because it's hard to see sometimes that they write it down as a triplet. So this is a triplet, meaning that this CH3 has to have a 2 hydrogen in the neighborhood, right? This CH3 has to have I'm sorry, 2 hydrogen in the adjacent carbon. So that's split into the triplet. And then I don't know what happened to that, but since it is a benzene, if we have a carbon that have a hydrogen there, this one is going to be somewhat de-shielded. Typical chemical shift, the benzylic position about 2.5. And then we do have a DCH2, the 2.5. So I think this is the one that connected to there. And then it's a two hydrogen, right? 2 hydrogen there. And this is also a triplet. What it means is that have a 2 hydrogen in the neighborhood. So if these two are the same things, and if I merge these structure together, then what is going to be look like? We have a benzene, and then these structures. So DCH2, that's the one that shows right there, and then that CH3, that's the one showing over there. And then the middle CH2 of the propyl groups, this is going to be very complicated because this is going to be split by this This is going to split by that. So it's just such a complicated splitting pattern. It's such a tight, small areas. So it's written as a multiplet. It could be a large number of the splitting. So can really figure out. So we just put it down as a multiplet. So that's a person, the middle CH2. So this is just a propyl group. So propyl group is not that much simple. This N, either N, this N or that N is a somewhat easy because we got triplets, but the middle ones like this is going to be really, really large splitting there. So this is a propyl benzene. Okay. So this is our third question. Let's move on. This one is the 7 carbon, right? So once again, D group unsaturation, 7 carbons, and then the subtract 13 half of the hydrogen and subtract half of the bromine. So we need to subtract that, and then plus 1. So that basically just 1 degree of saturations. So I don't know what it is. It says a 1 degree of saturation. Could be double bonds, could be circular molecule. But if you look at that 3000 line, there's nothing there. So I don't think there is a double bonds there. Well, could be cyclic structures, but and then we don't know. If it's a double bond, we should have some kind of a carbon double bond stretching signal there, but it's not there either. So I don't think it's a double bonds. But let's look at, and then we have a bromine there. I mean, we shouldn't forget there's a bromine here. I mean, this is a definitely clearly showing that there's a bromine in the molecule, but molecular formula also shows a bromine there too. Well, let's look at the carbon 13 NMR. We got how many carbons here? 7 carbon. We got 7 carbon, but do we see 7 peaks? Once again, this is coming from the NMR solvents, so this shouldn't be count. But we got 1, 2, 3, 4, 5. We got 5 peaks, not 7 peaks. What that means is there's a definite symmetry in the molecule. And then I don't see any hydrogen in the double bond area. So I don't think this is a double bond. This is a clearly circular molecule. And then the why don't these ones are somewhat deshielded? Probably these are 2 hydrogen, right? This is H2. This H2 is probably the one that having a bromine. That's why it's a deshielded. And the others are is kind of a I cannot make up whether there's a triplet, quartet, whatever. This is a lot of a peaks, 6 hydrogen, 5 hydrogen, all comes down together. So basically 11 hydrogens are all there. So how can you explain this type of massive, the messy, uh, the very aliphatic, right? Because it's very upfield. So what that means is this is a very aliphatic chain, and then this is CH2 there is it comes out. So let's find out. So C7, what's the molecular formula again? C7H13Br1. So C7H13 on bromine. So since we found out these bromomethylene groups, so that's a C1H2 and then 1Br. So what's left to us to find out the C6H11, right? C6H11. So 11 hydrogen that we need to find out is all there. That's 11 hydrogen there. It's kind of hard to find out. And the 6 carbon, and then there's a symmetry. So how can we figure out that? That is sort of like a pointing out we got cyclohexane structures. So that way we have a symmetry in the molecule. That's why the number of the carbon goes down. And then if the cyclohexane, these are all splitting very similar hydrogen, all splitting each other's. And then this is a rotation and is restricted. So these hydrogens are really, really hard to be just stands out. And then so that is basically showing this type of situation. So 1 hydrogen I mean, that's 11 hydrogen there. So then this one should be probably connected right there. So this is the structures. That way, only these 2 hydrogens are stands out because that's a deshielded by the bromine that's showing up right there. And then rest of all the hydrogen cyclohexane, the ring structures are they all comes in the very similar regions and split it with so many hydrogen axial equatorial. So it's not even easy to make up. And that's the only way we can have these structures. And then the less number of carbon peaks, suggesting that we have a symmetry, which goes right there. So we have a 5 signal. So let's make sure that we got 5 carbon here, 5 different carbon, 1, 2, 3, 4, 5 different carbon. Because this is same as that, this is same as this, we got 5 different carbon in the molecule. That clearly points out the 5 peaks in the carbon 13 NMR. So this is not quite a simple one, right? But at least you can see how we come to the solutions. Okay, moving on. The next one is a 5 carbon, 8 hydrogen, and 1 oxygen. So the degree of unsaturations, um, number of the carbon, half of the hydrogen, so 8 divided by 2 plus 1. So that will be 2. So we got 2 degree of unsaturations. So how can we get a 2 degree unsaturation, 2 double bonds, or maybe 1 double bond cyclic structures, or 2 cyclic structure? That's also possible. I don't know what it is. We have a double bonds at least. So these clearly show that we got hydrogen on double bonds. That's a CH stretching signal. And then because of 5 carbons here, I don't think this is a benzene. So we don't have a benzene. This is definitely double bonds. And then the 1640, that is a carbon-carbon double bonds. That's basically what it shows up. Not 1600, which is typically the benzene, the C double bond shows up. So we don't have that. So that's all we can say from here. So C5H8O. So I'll write down molecular C5H8O. So we have an oxygen there. So oxygen is not a carbonyl. So we don't have any carbonyl stretching signal down there. So there's no carbonyl. So we don't have a carbonyl. So what that means is that oxygen must be ether. So how can we figure out what it is? I mean, this is a kind of this could be confusing. I mean, 7 and 8, that's the aromatic signal, right? 5 and 6, that's the double bonds. This is a definitely belong to the double bond. So this is a 1 hydrogen each. So that means of this double bond, there's a 1 hydrogen there, there's another hydrogen there, but these ones are so deshielded compared to the other. So how do we support this idea that why one of the CH2 so deshielded? Probably that's the one next to an oxygen. So this hydrogen could be that one. Maybe this one is that one. Well, this is just a suggestion, but that is sort of supporting it. And then if you look at that, the four ppm CH2, something that goes down so deshielded region. I mean, the 4 is probably having oxygen next to it. So I'm just going to put it together. Then this CH2 probably there. So that CH2 is this one. So we sort of like figured that out partially, and then this is 5 carbon. Do we have a symmetry in the molecule? 1, 2, 3, 4, 5. So we got all 5 carbon peaks. So there's no symmetry in the molecule. At least we got double bonds, and then so that could mean that we maybe have a 1 double bond, 1 cyclic structures. And to support that, only thing missing. Let's find out how much. So we got how much. This structure we found out is a 3 carbon, right? And then how many hydrogen? 1, 2, 3, 4 hydrogen, and then 1 oxygen. So if we subtract that C3H4O, then that will be C2H4, which is CH2. I mean, that would be the one possibility. Another possibility, as we talked about, is the CH, and then this possibility. But if you look at that one, there's a 4 hydrogen. We don't have any methyl groups there. So it looks like a equally divided 2 hydrogen there, 2 hydrogen there. So I don't think this is a situation. We got CH2, CH2 is connecting those things together. So if you put that structure down, that will be oxygen, and then this basically, that would be the structures. So these CH2 there, that's the one over here. And then these hydrogen on the double bond next to an oxygen, that's the most deshielded one. And then this is the one that goes that one. And those 4 hydrogen, that's the one showing up there. Should be this one hard to make up. It's hard to say because that's going to be split by this one. That's going to split by that one. Those This is somewhat complicated, but this one is a probably split by this one, also split by that one a little bit. So they didn't say anything about, it's kind of hard to see because it could be very small coupling constant. But anyway, by the path, where the peak shows up, this is the only possibility. So I think this is a one. So that would be the answer for this question. And see question number 6. Okay, so this one is a C6H10. So it's a pretty simple degree of unsaturation again. This number of carbon subtract by the half of the hydrogen, and then plus one, and then that will be 2 as well. And we do have a double bonds. You can see that this is a carbon hydrogen stretching signal on the double bonds. And then there is a no carbonyl. I don't see any carbonyl there. So whatever, it doesn't have even oxygen there. So there's a no carbonyl even need to be concerned. It's just a carbon and a hydrogen with the double bonds there. So whether there's a two double bonds and the one double bonds and the circular structures, I don't know. We have to see. Um, it's a 6 carbon, right? So 6 carbon there. How many carbon peak do we see? One, two, three. We only see 3 peaks. So what that means is there's a definite symmetry. How come 6 carbon peak becomes a 3 carbon? I mean, signal. Oops, 3 carbon signal is a. We probably have a the these molecules are symmetrical. We have a plane symmetry molecule. So I'm gonna write down plane symmetry right there. Um, and then, since we have a double bonds, this certainly support that we have a double bond. And then this is double lead. If it is a proton is splitting the carbon, then this is double lead. What that means is this is CH. That CH is a splitting that one is double lead. So what that means is we have a double lead. This is symmetry, the plane symmetry. We got one hydrogen, and that means that we got hydrogen there too. But that is of equivalent. That's why we only see one. And then two carbon, then we're gonna have a 2 carbon there. And then this basically so triplet. What that means is that whatever this carbon, I don't know which one it has a 2 hydrogen, and the other also have a 2 hydrogen, and it's symmetrical. Otherwise, it cannot be that only small number of bond. So it's a symmetrical. So does this account for everything that we have with the molecular formula C6H10? So we got C6H10. So we got 6 carbon, and then if you count number of hydrogen, there's a 2, 4, 6, 8, and 10. So I think that is the molecule. So this one looked difficult, but if you consider symmetry, you may be able to figure it out because it's such a small molecule. There's only few choices for putting things together. All right, moving on. This one is a C10H7 and 1 bromine there. So degree of unsaturation, so number of carbon, 10. And then the half of the hydrogen, half the bromine need to be subtracted. Is 7 plus 1 divided by 2 plus 1. So that will be the 8, that's 4, 6. That will be 7. So this is quite a significant of the degree of unsaturation. If you think about it, 7. Huh, I don't know what it is. Again, we have a bromine. It's clearly also showing in the bromine isotope signal. I mean, we didn't do the mass spec, but this certainly support that one. And if you look at the NMR spectrum, this is over 3,000 line. So this is clearly hydrogen on double sp2 hybridized carbon. Could be aromatic double bonds or could be aliphatic double bonds. I don't know. Below 3,000, there's nothing much there. So what that means is that there's probably not much aliphatic signal there, and it's hard to say anything more than from this NMR. Well, C10H7BR. So C10H7BR. Well, if you look at the proton NMR, well, here's a nothing there. We got nothing there. So there's no aliphatic carbon there. It's all aromatic carbons, all aromatic carbons. And then same thing for the carbon 13. It's all aromatic. Every carbon is aromatic. And then we got one bromine somewhere in the aromatic ring. So how can we get the, first of all, let's think about the benzene. Benzene benzene takes up 4 degree of bond saturation, right? Because of the 3 double bonds and then 1 circular structures. If you have two benzene, put it together like this, then that will be 8 degree bond saturation. At the same time, this makes a 12 carbon. So we cannot have like that. This is not a possibility. Then we still need to come up with the 3 degree bond saturations. So what is going to be is kind of for this, you probably know some of the organic structures. This can be another ring fusing together. So we got 4 degree bond saturation, right? And then so by having a ring structure, that'll be 1 degree bond saturation, and then we got double bonds here, double bond there. This is a naphthalene. Naphthalene, and then two double bonds. So 3 degree bond saturation coming from the second ring. The second ring fused together. So add up this thing, that will clearly make up the 7 degree bond saturation we found out. And then the how many hydrogen it can have altogether is 1, 2, 3, 4, 5, 6, 7. There's 8 potential substituents. There's no way we can put the hydrogen there because these are all tetra substituted. So these are not contributing anything. So we got 7 hydrogen. 1, 2, 3, 4, 5, 6, 7. And then the last one is going to be the bromine. Well, the question is, I don't know where the bromine is going to go in these naphthalene structures. It's either this or it could be either the bromine in that position. We just cannot tell which one it is based on this NMR spectrum. So there's this so there's a two possibility. If someone were thinking that it could be more than that, how about bromine going down this? That is actually identical to that. If you're thinking about bromine on the other ring, right? That there, this is also same as that. I mean, bromine can also go there, which is the same as this. And then if this one is also equivalent to, so there's a lot of different positions to bromine go. This one is the same as the other one, right? Also potentially there, also potentially there. So there's only two possible isomers, structural isomers. You can come up with this. So, but which one it is, we don't know. This animal spectrum cannot tell us which one is the right one. But at least we can come up with a two possibility uh, for the answer for this question. Okay, question number 8. This is C8 H6O2. So degree of saturation. If you do that, there's 8 number of carbons, half of the hydrogen, 60 divided by 2, and then plus 1. So that's be 3, 5. That would be 6. So 6? No, 5. Oh, that would be 6. Right. Yes, that would be 6. I'm confused. Oh. So there's a 3, there's a 5 plus 1, 6. So it's 6 degree saturation. That's somewhat large. We got 2 oxygen there. So I don't know whether this oxygen is going to be ether or the carbonyl. How can we tell? Well, we have a CO stretching signal. I don't know what it is, but this thing is a very somewhat lower frequency compared to the normal carbonyl. Normal carbonyl is a 1710. This is a 1690. It's sort of like a 20 went down. And then what else is interesting is this 2800, 2700. That one is clearly showing that we have a aldehyde, right? This aldehyde hydrogen is basically showing that, and then this carbonyl of the aldehyde, and then it somehow is it is a conjugated. Because of its conjugated, um, it's a sort of like I mean, it doesn't necessarily double bond. It could be benzene too. But anyways, it's a next to the sort of unsaturated bond. That's why it came down. And I don't anyway having an aldehyde there. So 2 oxygen. So potentially 2 aldehydes or 1 aldehyde, 1 ether, or something like that. At least we have to have 1 aldehyde. So C8H6O2. C8H6O2. Okay, so we got 8 carbons, but if you look at the the carbon 13 NMR, 1, 2, 3. That's it. That's all we see in the molecule. So we have a definitely heavy symmetry in the molecule. So 8 pig, it could have been 8 pig if there's no symmetry. Now it becomes just a 3 pig. So we have a really significant symmetry in the molecule. And then we do have a type of benzene, 4 hydrogen in the aromatic region. So these clearly show that we have a 4 hydrogen on the benzene. So we do have a 4 hydrogen in the benzene. And then there's a 2 hydrogen in the that's a 10. I mean, it's kind of a little bit over 10, but this is the aldehyde hydrogen. And the aldehyde hydrogen only one there. So that means that we have to have a 2 aldehyde groups there. So first of all, C6 that the para-substituted benzene, or di-substituted benzene, if you want to say it that way, that's C6H4. So if you subtract that, that would be C2H2O2. So aldehyde is a CHO. So that means the 2 aldehyde is right there. That's the only thing left out. So this either end is going to be coupled to an aldehyde. I mean, both ends. So that will, so these 4 hydrogen of the benzene, because it's a symmetry, it's a very symmetrical, not only symmetrical here, but also symmetrical there. So each of all these hydrogen becomes an equal. That's why it only shows only the one signal. That also supports a para-substituted system, symmetrical para-substituted system. If it's not para-substituted, then this could have been most multiple pick, not just the one pick there. So this is a definitely high symmetry. You can see that not only one symmetry line, but also 2 symmetry line. It comes down the carbon 13 signal only number 3 picks, not 8 picks. Okay, so this is the answer for this one. Now the 2 questions left on this one. Let's go to the end. Let's do the degree of unsaturation. Number of carbon divided by half of the hydrogen, 6 divided by 2, and plus 1. So that would be 3, 4, 3, 4. That would be 5. 5 degree of unsaturations. And then what do we see? 2800, 2700. That is an aldehyde signal, right? That is an aldehyde. So we do have an aldehyde again. These are hydrogen aldehyde signal. And then do we have a and then also I forgot to mention that um, because of we have a aldehyde carbonyl next to benzene, that definitely support why these carbonyls are such a lower frequency, right? So I want to mention that. And then it's almost type of similar system here because it's a 16. Oh, it's a 1665. This one even go down more, huh? Anyway, this is 1665. These ones are also um, quite conjugated too. So whatever it is, it's very conjugated double the aldehyde carbonyl. And then, but this is a 3240, but anyway, close to 3300. That is an OH signal. We do have an OH. We do have an aldehyde. And then, I mean, these are carbonyl of the aldehyde. And then we have some kind of unsaturation there. So C7H6O2. So C7H6O2. So since we found an aldehyde, I'm going to subtract an aldehyde, CHO, right? And that will be C6H5O. And then there's an OH. We found our OH. So 1 hydrogen, 1 oxygen. So this is an aldehyde functional groups. Oops, we found out. And then this is an OH group we found out from the IR. So we subtract that one. Then C6H4 is what we need to find out. And then this 1 hydrogen exchanging, that is a definitely OH. And we don't have a carboxylic acid, so I don't think this is a carboxylic acid. If it's a carboxylic acid, then IR spectrum is not here. It's going to be centered like this. So this is carbonyl. It's definitely coming from the aldehyde, not the carboxylic acid. Somehow this OH is shifted significantly down here, right? That means that it makes a hydrogen bonding significant hydrogen bond. Oops, sorry. That means that this is a significantly hydrogen bonded hydrogen. And then this is an aldehyde between the 9 and 10. That's an aldehyde hydrogen, right? So we have an aldehyde. So both found. And then we got 4 hydrogen in the aromatic regions. I mean, that clearly looks like a disubstituted benzene. I don't know, two hydrogen, two hydrogen. It could be like this. There's a substitution point, and then it could be like this, or that could be either, if it's a meta substituted, then it could be like this, right? And then if it's also substituted, then it could be like this. And then I don't know what it is right now. I mean, I'm just gonna keep going and then trying to figure out what it is. That 192, that's the aldehyde carbonyl. And then from here to all the way there, that's basically aromatic hydrogen, carbon. So we got aromatic carbons. Um, but if you look at that, 7, 1, 2, 3, 4, 5, 6, 7. So we have all 7 carbon peak shows up. What that means is there's a no symmetry. We have a no symmetry in the molecule. If it's a parasubstituted like this, then it will be symmetrical. So that means that we should have a less number of carbon peak. So that excludes this possibility out. So either the also substituted, right? These are also substituted, or the meta substituted. I don't know what it is, but at least it is either those two. And then the C6H4 is basically all the things that we need to find out. So basically that's it. So the possible structure is if this is an aldehyde there, then either hydroxyl groups in the meta position, or if you put an aldehyde there, and then we got hydrogen in the other position. So which one of those two will be the one that we have here is kind of hard to figure out, but there's some clue here. One, two hydrogen sort of grouped together, right? It's not, if this is if this is the meta situation, you can see that there's only one hydrogen sit alone. There's only one hydrogen. Oops. I guess I went back. There's only the one hydrogen is sitting alone. So that should be standing out as one hydrogen, and we don't see that. So I don't think this is a case. So if that's the case, we got 4 hydrogen somewhat groups together. So maybe, I don't know, two hydrogen, somehow separated out like this. But what is supporting this possibility is there is a hydrogen bonding, significant hydrogen bonding you can expect from this hydrogen to the carbonyl of the aldehyde. This clearly showed that why this was so deshielded. This comes out, I mean, normally the OH comes of this region is next to the the benzene, so it can shift even further more, but even go more than that. So why is it so deshielded? Because it's a hydrogen bonded to the carbonyl next to an aldehyde. So because of that, I think the answer is this one. All right, the next one, the last one is we have a C9, so 9, the degroup on saturation. We got the 9 carbon, right? C9, and then half of the hydrogen, so which is this, and then plus 1, so that'll be 4. I mean, this is 5, this is 4. So we got, oh, wait a minute, 4, 5. We got 5 degree of saturation. So that is a pretty large. We got 5 degree of saturations. And then if you look at the signal, this is a really broad signal, very broad. So I think we have a carboxylic acid. Carboxylic acid is in the molecule. And this 1701 is this carbonyl. At the same time, this is also somewhat lower frequency. So we may have some kind of unsaturation, double bonded probably next to it. Um, I don't know whether this double bonds or benzene, but this is something next to it, or, or possibly. I'm not exactly sure, but at least there's a possibility. If it's a double bond, this should be probably go down a little bit more. It looks like it may not be a double bond. That is just I mean, maybe happen to be just 1710. If it's double bond next to it, probably fall down to maybe 1680 or 90. I don't think 1701 support having a double bond next to it. Anyway, well, let's look at the possibility. from the NMR. So C9H10O3. So C9H10O3. At least we found out the carboxylic acid, C carboxylic acid there. And then these one hydrogen very exchangeable into such a high chemical shift. This definitely support the carboxylic acid there. So let's find out if we substitute of C1, O2, H1, then we got C8, H9, and O1. So we still need to find out one more oxygen where that could possibly come from. Um, if you look at that in the this system here, we do have a benzene, and this clearly support the para-substituted benzene because of the pattern of the chemical shift, right? So we got this para-substituted benzene in the molecule, so that would be C6H4. So let's substitute C6H4. Once you take it out, that would be C2H5 and O1, right? That's all. Yeah, that's what is left out. That's a para-substituted benzene is what we just take it out. Okay, and then we had a 5 degree of unsaturation. So we got 5 degree of unsaturation, and then carbonyl have a 1 degree unsaturation. So that basically 4 degree unsaturation left out. Benzene is a 4 degree unsaturation. So finally, we found out all the unsaturation in the molecule. So carbonyl we found out, benzene we found out. That's all the unsaturations. So whatever the oxygen left out, it cannot be the part any carbonyl. So that means that has to be ether. So oxygen has to be bonded to um, something. And then clearly we got 3 hydrogen, that is a CH3, and then it's a singlet, and then it's such a de-shielded region. So that means that these methyl groups have an oxygen next to it. That way, it's a singlet, is a de-shielded significantly. And this CH2 is a somewhat very de-shielded too. So that's a CH2 potentially having something like an oxygen next to it, something very electron withdrawing is next to it. Um, also support that this carbon next to the oxygen is supported by this. If this is also next to an oxygen, that should be also somewhere in these regions. But we only see the one carbon oxygen peak in these regions, right? So that means this may not be the oxygen next to it. Just a electron, such an electron withdrawing. Maybe the benzene is playing a role as such electron withdrawing groups, or maybe between some other electron withdrawing groups, like a carbonyl, right? Carbonyl is also electron withdrawing groups, but if it's next to the benzene, those two combination can bring this H2 down this much. It may not, it is not an oxygen because we don't see the carbon oxygen signal pick two of them. We only see one. So that means that we got only one next to an oxygen as an ether. So how are we gonna put it together? So benzene, right? We got benzene, para-substituted benzene, and then one oxygen bonded, and we got CH3. That's the what we found out there. And then what is left to CH2, right? CH2 there is CH2, and then we have a carboxylic acid. So that way, this CH2 is a somewhat de-shielded because it's a benzylic position. Just the benzylic position is 2.5. Chemical shift is 2.5, and then next to carbonyl is probably add one more, so it's about 3.5. I think that's a little bit more further down, but that's sort of like explain why this H2 is a de-shielded, almost like a next to an oxygen, but it is not the next to an oxygen because we don't see the two carbon peaks uh, in the next to an oxygen there. So I think this is a possibility. If you don't look at that, and then potentially you may get a answer like this. If you put that one as next to oxygen, then you put CH2 right there, and then double bonds, and then there is a carboxylic acid. If this is the case instead of the other one, then this carboxylic acid carbonyl is conjugated. If that's the thing, if it's conjugated, then it's a 1701. It's kind of a little bit smaller, but I don't think this is just not. I mean, if it's a carbonyl, benzene there, and then carbonyl carboxylic acid right there. If this is the case, then I think that'll probably 1680. It's gonna be below 1690 in my opinion. That just little too small differences from the normal 1710 numbers. So I don't think this is the conjugated carboxylic acid. So and then also what clear supported is we only have a one carbon peg for the one carbon next to an oxygen. So if this is this case, then this explain two carbon has to be next to an oxygen. So we should have a two peaks there, but we have only one. So clearly say that this is not the case. So it should be this one. So I hope that you get an idea that how to solve the problems of the NMR, considering many things together. So this is definitely some of the questions are challenging, but going over this thing, I bet you can learn a lot. And then even the numbers that you see in the table, like the chemical shift, and then the stretching bands frequencies, you can see how those things you need to use to get to an answer. At the same time, to come up with the actual structure of the molecule, you really need to pay attention. That's the where the carbon 13 can shine. The number of the carbon 13 peak can tell us whether the molecule is a symmetry or not. So this thing is very useful tips if you can find out from the questions. Okay, I hope that this can help you studying.